Hello everyone. In this presentation, I'll be reviewing the entire support vector machine Python code. I'll go over each part in detail so that you gain a clearer understanding of how it functions. So, without further ado, let's begin with the first slide. In the first line of code, the function fetch openML is imported from scikit-learn's dataset module. This function is essential for fetching datasets directly from the OpenML platform. By doing this, you're leveraging a highly convenient way to access pre-existing datasets without needing to manually download or process them beforehand. The second line of code loads the mice protein dataset by using the fetch openML function. The parameters here define the dataset to be loaded, specifying the name as mice protein and version 4. You also set as frame = true, which ensures that the dataset is returned as a pandas data frame. This is very useful because data frames allow you to manipulate data in a highly structured and intuitive way, similar to working with Excel sheets, but far more powerful. In the third line of code, the function list mice.frame.columns lists the column names of the data frame. This gives you a quick view of all the features in the dataset. Listing the columns is a typical first step when exploring a dataset, as it provides insight into what data points or variables are available for analysis. The final two lines of code are commented out. The print mice.details would likely give detailed information about the dataset, like its shape or other metadata, while mice.frame.describe would provide summary statistics for all numerical columns in the data frame, such as mean, standard deviation, and percentiles. This is a useful step in understanding the general characteristics of your data before jumping into any pre-processing or modeling tasks. This snippet is essentially setting up the environment to work with a neural network using Python. Let's walk through each part of the code. The first line imports NumPy, one of the most widely used libraries in Python for numerical computing. It's being imported as NP, which is the standard alias that makes it quicker to reference NumPy functions. NumPy provides support for working with arrays, performing mathematical operations, and handling multidimensional data efficiently. In the context of neural networks, NumPy is often used for handling datasets, performing operations like matrix multiplication, and more. Next, you see the sklearn import, which is the alias for the scikit-learn library. Scikit-learn is one of the most popular libraries in Python for machine learning. It provides a vast number of tools and algorithms for building, training, and evaluating machine learning models. This library makes it easier to implement common models like decision trees, support vector machines, and neural networks with a clean API. Finally, the most critical part of this code, the import of MLP's classifier from the neural network module within scikit-learn. MLP's classifier stands for Multi-Layer Perceptron Classifier, which is a type of artificial neural network. This particular classifier is used for supervised learning tasks, where the goal is to predict a discrete label for input data. The model works by using multiple layers of perceptrons, which are just simplified artificial neurons, and can be used to classify complex data patterns that linear models might struggle with. So essentially, this snippet is preparing to build a neural network that can be trained to classify data into different categories by using NumPy for data handling and scikit-learn for model creation. This kind of setup would be common in tasks like image recognition, text classification, or any other type of machine learning task that involves labeling data. This snippet focuses on splitting data into training and testing sets. In machine learning, it's crucial to divide your data so that you can train a model on one portion and evaluate its performance on another portion that the model has never seen before. This helps to generalize the model and assess how well it might perform on new, unseen data. In the first line of code, you're importing the train-test-split function from scikit-learn's model selection module. This function is specifically designed to help you randomly partition your dataset into training and testing sets. It's a key part of building machine learning models because it ensures that you have a reliable way to test your model's performance after training. when you call train test split, you can specify how much of the data should go to training and how much should be set aside for testing. For example, you might allocate 80% of the data to training and 20% to testing, which is a typical split. You can also shuffle the data before splitting to ensure randomness, which is helpful when your data has an inherent order that might skew the results if not randomized. By splitting the data this way, you're setting up a framework to train your model on a subset of the data and then test how well it performs on a separate subset, making sure your model doesn't overfit and is capable of generalizing to new data. In this code, you are preparing the dataset for machine learning by selecting the target variable or label, identifying the predictor columns, features, and standardizing the data. Let me walk through each step, referring to the lines of code. The first line of code defines the target column, which is the column containing the class or label you want to predict. In this case, the target column is named class. This is typical when you're dealing with a classification task, where you want the model to learn from the data and assign class labels to new instances. In the second line of code, you're deriving the list of predictor column IDs by first listing all the columns in the data frame and then removing the target column. You use the set function to handle this process. It subtracts the target column from the full set of columns, leaving only the predictor variables. This operation ensures that you don't accidentally use the target column as part of your input features, which would result in data leakage and give your model unfair advantages during training. The third line of code standardizes the predictors by dividing each feature by its maximum value. Standardization is crucial in machine learning as it normalizes the feature values, bringing all of them into the same range, in this case, between 0 and 1. This ensures that no single feature dominates the model just because its values are larger, which is especially important for algorithms that are sensitive to scale, like neural networks. Finally, in the fourth line, you provide summary statistics for the data frame. The described TR function gives key statistics like the mean, standard deviation, minimum, and maximum for each feature. By using the .transpose (C) method, you're switching the rows and columns of the summary output, making it easier to read the summary statistics for each feature across the data frame. Overall, this code is part of the pre-processing steps in a machine learning workflow, where you prepare the data for modeling by selecting predictors, normalizing them, and understanding their distribution through summary statistics. In this snippet, the goal is to clean the dataset by removing any rows that contain missing values. The first line is a comment that states the intention, to get rid of rows with missing values, which are represented by NA in the data frame. The second line of code accomplishes this by using the dropNum method from the pandas library. This method works on data frames and removes any rows where at least one element is missing. Here, you are calling it on the mice frame data frame, which represents the dataset you're working with. After applying dropNA, the data frame is reassigned back to mice.frame, overwriting the original data. By doing this, you're ensuring that any rows with missing values are excluded from further analysis or modeling. This step is crucial because many machine learning algorithms cannot handle missing data directly, and removing these rows is a common pre-processing technique when you don't have strategies in place to impute or fill in those missing values. However, it's worth noting that depending on the dataset, dropping rows with missing values might lead to loss of valuable data. So this technique is typically used when the proportion of missing data is small or non-critical. This code snippet is preparing the data for machine learning by separating the input features, or predictors, from the target variable, or output. Let's go through the process step by step. In the first line of code, X is being defined as the input data. Here, mice.framePredictors selects all the columns that were identified as predictor variables earlier in the code, the features that will help predict the target variable. The .values attribute extracts the underlying NumPy array from the data frame, which is often needed for compatibility with machine learning models, especially those from scikit-learn that expect NumPy arrays as input. In the second line of code, y is defined as the output data, or the target labels you want to predict. Mice.frame, target underscore column, selects the column that contains the class labels, in this case the column you identified as class. Again, the .values attribute extracts the raw NumPy array of values. To summarize, X contains the features, or predictors, and Y contains the target labels, or output. Both X and Y are now in a format that's ready to be fed into a machine learning model for training. This is a typical step in supervised learning tasks, where you need to clearly define what the model will learn from the features and what it needs to predict. In this snippet, you're encoding the target variable, which may contain categorical labels, into numerical values using scikit-learn's label encoder. This is important because many machine learning algorithms, particularly neural networks, require numerical inputs and outputs rather than strings or categorical data. The first line of code imports the label encoder from the pre-processing module of scikit-learn. The label encoder is a utility that transforms categorical labels into numerical labels. It is especially useful when your target variable contains classes represented by strings, for example, cat and dog. This encoding is necessary since machine learning algorithms can only interpret numerical values. In the second line, an instance of the label encoder is created and assigned to the variable li. This instance will be used to transform the target variable into numeric form. The third line of code uses the fit_transform method of the label encoder. This method first learns, or fits, the mapping from the original string labels to numeric labels, and then applies the transformation to convert the labels into numbers. The result is stored back in the variable y, which is your target variable, now encoded as numbers. In summary, this process ensures that the target variable y is converted from strings or other categorical formats into numerical values, which is essential for feeding the data into neural networks and most other machine learning models. In this snippet, you're dividing the dataset into training and testing sets, which is a common practice in machine learning to ensure that the model can generalize well to unseen data. In the first line of code, the train-test-split function from scikit-learn is being used. This function splits your features and target into training and testing sets. The parameters passed include x, which are the input features, y, which is the target variable, and test size equals 0.30, which means 30% of the data will be set aside for testing, and the remaining 70% will be used for training the model. In the second line of code, xtrain.shape and xtestshape are printed to check the dimensions or shape of the training and testing input data. The shape attribute gives the number of rows and columns in the dataset, which helps you verify how the data was split. This step is crucial to ensure that your training and testing sets are properly split and that the correct proportion of data has been allocated to each set. This split will be used to train your model on the training data and evaluate its performance on the testing data. In this code snippet, the SVM module is being imported from the scikit-learn library. SVM stands for Support Vector Machine, which is a powerful and widely used machine learning algorithm for classification, regression, and even outlier detection. By importing SVM from scikit-learn, you're setting up your environment to use the Support Vector Machine models provided by the library. SVMs are particularly well suited for classification tasks where you want to find a hyperplane that best separates different classes of data points. In high-dimensional spaces, SVMs are effective because they aim to find the maximum margin separator between the classes, which leads to robust decision boundaries. Once the module is imported, you can create instances of different SVM classifiers, such as the basic support vector classifier or the support vector regressor, depending on whether you are working on a classification or regression problem. This code is setting up and training a support vector classifier model using scikit-learn's SVM module. In the first line of code, an instance of SVC is being created and assigned to the variable SVM_model. The argument decision_function_shape equals ovo specifies that you are using the 1 vs 1 strategy for handling multi-class classification. In the second line of code, the fit method is called on the SVM model, using the training data to train the classifier. The fit method is standard for training machine learning models, and during this step, the model learns how to separate the data into classes based on the features provided. After calling fit, the SVM underscore model will be trained and ready to make predictions on new, unseen data by using the predict method. In this code snippet, predictions are being made on both the training and test datasets using the previously trained SVM model. In the first line of code, you are predicting the labels for the training set. The predict method is used to make predictions based on the input features that were used during training. This step will output the predicted labels for each instance in the training set and store them in the predict underscore train variable. In the second line of code, predictions are made on the test set. Here, the predict method is used again, but this time with the unseen test data. The resulting predictions for the test data are stored in the predict underscore test variable. By predicting both the training set and the test set, you can later compare the predicted labels with the actual labels to evaluate how well the model performs both on the data it was trained on and on the unseen data. This code snippet imports two evaluation functions, classification report and confusion matrix, from scikit-learn's metrics module. These are important tools for assessing the performance of your machine learning model, especially in classification tasks. The classification report is a function that generates a detailed report showing key metrics like precision, recall, F1 score, and support for each class in the dataset. This report gives you a more nuanced view of how well your model is performing across each class, not just an overall accuracy score. Precision measures how many of the predicted positive instances were actually positive, while recall indicates how many actual positive instances were correctly predicted by the model. The F1 score is a harmonic mean of precision and recall, providing a single measure that balances both. The confusion matrix function outputs a matrix that shows the true positives, true negatives, and false negatives for each class. This matrix helps visualize where the model is making mistakes by showing how often one class is confused with another. Each cell in the matrix corresponds to the number of instances where a specific class was predicted versus the actual class. Together, these tools are commonly used to evaluate the results of a classifier, giving a more detailed understanding of its performance beyond simple accuracy. In this snippet, you are evaluating the performance of the SVM model on the training data. The code reports the confusion matrix and the classification report to assess how well the model fits the training set. First, the string training accuracy is printed to provide context for the upcoming evaluation metrics. This helps distinguish the training set results from the test set results, which are likely reported elsewhere. Next, the confusion matrix is printed by calling the confusion underscore matrix function. This matrix gives a breakdown of the number of correct and incorrect predictions across each class. It helps you see where the model is getting predictions wrong, specifically showing instances of false positives, false negatives, true positives, and true negatives for each class. Lastly, the classification underscore report function is called, which prints various accuracy metrics such as precision, recall, and the F1 score for the training data. These metrics provide a detailed view of the model's performance across each class, helping you understand how well the model is identifying each category. Precision tells you how many of the predicted positive results were actually positive. Recall shows how many actual positive results were correctly predicted. And the F1 score balances both precision and recall. This evaluation process is crucial in machine learning because it gives you deeper insight into the model's strengths and weaknesses beyond just accuracy. The confusion matrix helps you understand which classes are being confused, while the classification report provides specific metrics for each class, giving you a more granular view of the model's performance on the training data. This snippet mirrors the previous one, but it evaluates the model's performance on the test set instead of the training set. The first line prints testing accuracy, to indicate that the following metrics are for the test data. This is important to distinguish the results from the training accuracy that was reported earlier. Next, the confusion underscore matrix function is used to generate and print the confusion matrix for the test set. This confusion matrix will give you a detailed look at how well the model is performing on unseen data, showing where it gets predictions right and where it makes errors. Following that, the classification underscore report function is used to print out precision, recall, and F1 score for each class in the test set. As with the training data, these metrics provide a deeper insight into the model's performance on each class in the test data. Precision indicates how many of the model's positive predictions were correct. Recall shows how well the model identified all positive instances. And the F1 score gives a balanced measure of both precision and recall. Evaluating the model on the test set is crucial because it tells you how well the model generalizes to unseen data. The results here will give you a more realistic estimate of how the model will perform in the real world, as opposed to just evaluating its fit on the training data. If there's a significant difference between the training and test set performance, it might indicate that the model is overfitting to the training data. This output shows the performance of your model on the training set through a confusion matrix and classification report. Let's break down each section. Let's review the confusion matrix first. The matrix at the top represents the confusion matrix for 8 classes, 0 through 7. Each row corresponds to the actual class, and each column corresponds to the predicted class. For example, the first row means that all 29 samples of class 0 were correctly classified as class 0. The same pattern is seen for the other rows, indicating that almost all samples were classified correctly. The confusion matrix reveals that your model made very few, if any, classification errors on the training set. This often suggests strong performance, but could also indicate overfitting if the test set performance is significantly worse. Now, let's review the classification report. The table below the confusion matrix summarizes key metrics for each class, including precision, recall, F1 score, and support. Precision. For all classes, precision is 1.00, except for class 2, where it's 0.96. This means the model is very accurate in predicting positives for most classes. Recall. Similarly, recall is 1.00 for all classes, except for class 6, where it's 0.95, indicating that the model retrieved most of the true positives for all classes except class 6. F1 score. The F1 score, which is a harmonic mean of precision and recall, follows the same pattern, 1.00 for all classes, except for class 2, 0.98, and class 6, 0.98. Support. This column shows how many samples belong to each class. For example, there are 29 samples in class 0, 50 samples in class 1, and so on. And lastly, let's explore the summary metrics. Accuracy. The overall accuracy is 0.99, which indicates that 99% of the samples in the training set were correctly classified. Macro average. This averages precision, recall, and F1 score equally across all classes, giving you a class-level performance overview. All macro averages are 0.99, reflecting high performance across all classes. Weighted average. This takes into account the support for each class when calculating the average, and the weighted averages are also near 1.00, reflecting strong performance across the training set. In summary, the model performs exceptionally well on the training data, with nearly perfect precision, recall, and F1 scores across all classes. However, you should compare these results with those from the test set to check if the model generalizes well and isn't overfitting to the training data. This output shows the model's performance on the test set with both a confusion matrix and classification report, similar to the training set evaluation. Let's break it down. Let's first review the confusion matrix. The confusion matrix at the top provides insights into the test set's classification results for the 8 classes. For example, the first row indicates that out of 16 samples in class 0, 15 were correctly classified, but 1 was misclassified as class 6. This matrix highlights a few misclassifications, but overall shows strong performance with mostly diagonal entries, where correct predictions are made. Now, let's review the classification report. The table below the confusion matrix shows the precision, recall, F1 score, and support for each class. Precision. Most classes have a precision of 1.00, meaning that when the model predicts a certain class, it's almost always correct. However, class 2 has a slightly lower precision at 0.94, indicating some false positives. Recall. The recall is also quite high, with values of 1.00 for most classes, except for class 0, 0.94, and class 1, 0.96, meaning the model missed a few true instances for these classes. F1 score. The F1 score balances precision and recall. Classes 0 and 2 have F1 scores of 0.97, while the other classes have scores of either 1.00 or 0.98, showing overall strong performance. Support. This column shows the number of instances for each class in the test set. For example, class 0 has 16 instances, class 4 has 29, and so on. And finally, let's review the summary metrics. Accuracy. The model achieved an accuracy of 0.98 on the test set, meaning 98% of the predictions were correct. Macro average. The macro average of precision, recall, and F1 score is 0.98, showing that the model performs well across all classes. Weighted average. The weighted averages also sit at 0.98, which takes into account the number of samples in each class when calculating these averages. In summary, the model performs very well on the test data with an overall accuracy of 98%, precision, recall, and F1 scores that are consistently high across the board. While there are a few misclassifications, for example in class 0, the model generalizes well to unseen data, indicating that it isn't overfitting to the training set. This is a great result, showing that the SVM model has learned the patterns in the data effectively while maintaining strong generalization performance. We've come to the end of the presentation. It's been a pleasure walking you through the entire Python code. I truly hope you now have a solid understanding of it. If you have any questions, feel free to email me. Have a wonderful day.